Thank you, Jurek. It's a great pleasure to be here and speak at the conference celebrating your birthday. I'm going to talk about some joint work with Paul Tod from Oxford and also some work in progress with Paul. Thinking back of Jurek, I mean, my recollection is that we met in 1995. I was still a master's student in Poland. This picture was taken in Pune in '97, which was one of the GRG conferences. You can see some known players also from this morning's lectures. There's Roger, there's George. I haven't changed, Jurek. I'm also on this picture. Now, this is 22 years ago, and Jurek has influenced me in more than one way in these years. We have now adopted the same hairstyle, but there is more to it. So I'll be, I tell you about other links. I mean, my recollection, one recollection from this conference was that Jurek, I formed an opinion of Jurek as a very cautious man. This was in Pune. We would walk down the road full of street vendors. And Jurek was afraid of bugs, infections he can get, so he would walk in the middle of this road, not turning left nor right to keep the optimizing his distance, maximal distance from the vendors. Then I got to know him better. I saw him in action skiing, and I decided he's not that a cautious man after all. Now the work. So I'm going to talk about what will start off as a very old-fashioned subject and way of thinking of manifolds and conformal geometry. I'll talk about embeddings and isometric embeddings and what we call conformally isometric embeddings. But the starting point is how one thinks about manifolds and how one used to think about manifolds. And the 19th century perspective was what we would now call extrinsic. So you could think of a surface, like the one on the picture, as an embedded surface, embedded in R3. You could also think of manifolds as surfaces, but of higher codimension. So you could start with some ambient space, maybe R4, and impose two algebraic conditions, not one, also get a surface. And so on. I'm just talking about the manifolds. There is no metric structure or distance whatsoever. The way we think about manifolds nowadays, and we teach students, is say abstract. It involves coverings by open sets and collections of these open sets, atlases, which can fit together. And that is, if you taught manifolds this way, you might find it counterintuitive and might find it difficult to relate it to this way of thinking about manifolds, which is regarded as old-fashioned. But fortunately, there is a theorem to that respect, known as the Whitney embeddings theorem, which I think in its strongest form states that any n-dimensional manifold can be embedded in R capital N as a surface, not necessarily as a hypersurface, but as a surface where capital N is at most 2 times little n. And this, this bound is sharp, so there are manifolds, projective spaces, which you cannot embed in fewer than twice the dimension. So this theorem and this picture is about manifolds. Now, our interest in relativity is in Riemannian or in pseudo-Riemannian manifolds, where you might not only want to embed a manifold, but also deduce the notion of a distance from the embedding function. So there are two ways to think about it. Either you start off with a pseudo-Riemannian or a Riemannian manifold with a metric, and you ask yourself a question, can you embed this isometrically in some flat space? That is, there is not only embedding as a manifold, but the metric induced by an embedding agrees with your metric. Or you can take a view that the embedding functions start playing a dynamical role, and I think this was a view taken and then abandoned for some reasons in relativity in the 70s, that you think of Einstein's equations, if you like, as equations on the embedding functions. Okay? But that's what an isometric embedding is. So you have a map from a manifold to Rn such that the pullback by this map of a flat Minkowski or Euclidean metric, depending on the signature, agrees with your metric G. Now, there is a folk theorem, a folk saying, in that any two-dimensional surface with a metric can be at least locally isometrically embedded in R3. And indeed, that's how at least we in Cambridge teach surfaces to students. We start off with surfaces which are embedded in R3, such that the notion of a distance is just obtained from a Euclidean distance in R3. And that is, that needs a proof, and that is true. And there is an improved folk saying, which actually is a theorem, goes under the name of Cartan-Janet theorem, and applies to any dimensions under assumptions. So it's a local theorem, but it assumes real analyticity of the metric, and it states that any real analytic Riemannian or a pseudo-Riemannian manifold of dimension little n can be embedded in isometrically in capital N dimensions, where n it is at most given by this expression, right? So you will always find the local embedding in n times n plus 1 over 2 dimensions, and you might find embedding in fewer dimensions. And that, so if you put little n equals to 2, you'll find that capital N is 3 or less. Now, you can ask, if you are mathematically minded, and which I will not talk too much about this point, is under what conditions you can embed in fewer than this. So this is the maximal dimension you can always embed in. Can you ever embed in a fewer number of dimensions? And generically, the answer to that is no, you cannot, and you expect some curvature holonomy type obstructions, and they are hard to come by. The subject was initiated by Tracy Thomas in 1920s, and I wouldn't say demolished, because there are still open problems about this, but substantially developed by Brian Griffiths and Berger in the 80s. Now, this is all local. You can then ask about global. So, let's say you have a space-time with a singularity structure like maybe Kerr metric or Schwarzschild or others. Can you embed patch by patch so that these patches can be glued globally to form a manifold? And that's a different type of problem, which was in the Riemannian case solved by Nash. This is the John Nash Economy Nobel Prize winner, and in the Lorentzian case, and also Riemannian improved by Clark. And so Clark adopted Nash's. So what Clark did is he made Nash's paper readable to theoretical physicists. He simplified the proof and he adopted it to Lorentzian signature under the assumption that the embeddings of a class C3. And you see, if you follow these papers and Clark's proof in particular, you find that the upper bound for a dimension of a global embedding is this number. And it's not the kind of number you want to spend too much time thinking of, except to realize that it is a big number. So if you put m equals 4, little m equals 4, this number is, I think, 87 or 89. So, it's a theorem, but for all practical purposes, you might say, can I really learn something about four-dimensional spacetimes by embedding them globally in 87 dimensions? However, luckily, often for interesting spacetimes, we want to understand this embedding class, which I'm just about to define, is smaller. So now, I'm defining an embedding class of a pseudo-Riemannian manifold, which can be a global or a local embedding class, to be the smallest integer, capital N minus little n. So I need to take the smallest number of dimensions I can embed the space-time in, and having determined that, I take a difference between this number of dimensions and the dimensions of my space-time, and I call that embedding class. It's a kind of invariant. Now, what do we know about these embedding classes for metrics we would like to know about? So let's start with Schwarzschild. So the local embedding class turns out to be 2, and that you can see that by an explicit calculation done by Kastner, who's embedded Schwarzschild locally in R6. In fact, he has done it in R6 with signature 4-2, and Kastner's embedding doesn't go all the way to the singularity, so it doesn't go through the horizon. It becomes singular at r equals 2m. At the time, the nature of the horizon was not appreciated, but the formula Kastner writes wouldn't go through what we now call the horizon. Turns out that the global embedding class of Schwarzschild is also 2, and that was proved by, again, an explicit embedding of Fronsdal. See, Fronsdal, if you compare Kastner's and Fronsdal's works, you'll see that Fronsdal very cleverly, analytically continued Kastner's embedding and combined it on both sides of the horizon. In fact, if you really read what he writes and look at the date, I think he's someone who should have been given more credit for the discovery of Kruskal maximal extension. He writes in a footnote of his paper that he's been sent a preprint, one or other, with similar calculations, but the work was done in pretty much the same time, and it does extend the black hole. Now, you can ask the same kind of questions for Riemannian manifolds. What is the embedding class, local and global? And so one, what sort of Riemannian manifold would you want to understand? Well, to my mind, one of the simplest, interesting non-flat, non-conformally flat Riemannian manifolds in dimension 4 is the Fubini's 2D metric on a complex projective space. So this is, it's a symmetric space. You can understand all there is to be understood about a curvature by Lie algebras, Lie groups. You can find geodesics. So you might think, if there is a manifold where you can say what this embedding class is, it'll be that. But rather surprisingly, the embedding class is still not known for this complex projective space. And it's neither local nor global results are known. It is known, you see, that you can embed CP2 isometrically in R8, and you can actually write this embedding down explicitly. It is also known that you cannot embed it in R6, even locally. So there are local obstructions. So the open problem there is whether you can embed it in R7. Okay? Now, I'm going to move away from these isometric embeddings, and I talk about conformal isometric embeddings. So what are they? Well, so I'll say that a Riemannian, pseudo-Riemannian manifold can be embedded conformally in Rn with some signature if a metric in the conformal class of little g can be isometrically embedded in Rn. So that's one way to phrase it. Here I say I have an immersion from M to Rn such that the pullback of the flat metric from R capital M by this immersion is not necessarily G, but is in the conformal class of G. So it differs by G by a non-zero multiple. And so what, again, you could talk about embedding class for conformal isometric embedding, and you can look at examples and obstructions, and I tell you why you would want to do that. The only absolute theorem I know in this subject is by Jacobowitz and Moore, and that, as Cartan, it assumes its local result, assumes real analyticity, and it states that the conformal isometric embedding is always possible in dimension capital N, which is equal to n times n plus 1 over 2 minus 1. So the number of dimensions you need is one less than for isometric embedding. I'm going to give you a kind of intuitive and rather crude argument of this numerology. Why is this number something you would expect? So you see, let's say that you want to construct a conformal embedding explicitly, what would you do? You would think of, you embed in R capital N. So you need n embedding functions, call them x1 up to xn. And this x1 up to xn depend on local coordinates on M. And you see, you now take the flat metric, the one I called eta, and you pull it back. So, which means in real money, you just use the chain rule to compute what it restricts to. And you want this to be in the conformal class of G. So you write this system of first order partial differential equations, and then you count how many equations you have and how many unknowns you have. And you see how many equations are there. Well, the A and B are free indices, so there is, and they're symmetric. So you have little n times n plus 1 over 2 first order PDEs. How about unknowns? Well, the embedding functions are the unknowns, but so is, and that's the key point, so is this omega, this conformal factor. So the number of unknowns is capital M plus 1. Now, naively, but as the Jacobi's and Moore show also correctly, you would say that this problem will be solvable if the number of equations equals the number of unknowns, and that gives you this result. But it really needs a proof, because see, these equations are not in what's called involutive in the kind of PDE language. So it might be that there'll be some consistency conditions you get from differentiating these equations, and you have to show that there are, and then that's what the Jacobi's Moore paper does. So what will I do in the rest of this talk? Well, I'm going to discuss in painful detail a global conformal embedding of the Schwarzschild metric in R5. So it turns out you can do it globally in R4 plus 1. You can write down the embedding and you can prove that it's regular everywhere, goes all the way down to the horizon. I'll discuss obstructions to existence of conformal embeddings of class 1. You see, you have this number coming from the Jacobi's theorem, a big number of dimensions. Maybe some spacetimes like Schwarzschild can be embedded as a hypersurface. And you would not expect that to be true generically, but you would want to know what are tensor obstructions. And I'm going to give you some of those. And finally, I'll make some connections with physics, and I'll argue that once dust settles and you've constructed these conformal isometric embeddings, and the space-time you're embedding is a black hole, well, Schwarzschild really, to be honest, because that's where the calculation was done, then the Hawking temperature associated to this space-time can be compared, and in fact is equal to the Unruh temperature of the accelerating observer of the embedding. Okay, so now I'll give you some details. I'm going to talk about class 1 conformal embeddings. So these are those where, the simplest class, where you want to conformally embed your space-time as a hypersurface. And the way you do it is you're seek an isometric embedding not of a given G, but of a metric conformally related to G, where at this stage you leave the conformal factor unspecified. So if I write a tensor and it has a hat over it, that tensor refers to this conformally rescaled G. What I do is I compute a second fundamental form of this embedding, assuming that it exists, and I decompose it into a pure trace and trace-free part. Okay, so again, I put hats over this symbol, and this is the traceless part of the second fundamental form. Now, in this and next slide, but only, well, these two, I'll use spinors, two-component spinor notations. See, the advantage of decomposing the second fundamental form into a trace and trace-free part is that the trace-free part has a simple transformation rules under conformal rescaling. So see, the val tensor with one index up and three down is conformally invariant. That's the corresponding val spinor, and that's how this traceless second fundamental form transforms. So one theorem which we can prove is that the necessary and sufficient conditions for the existence of a local conformal embedding such that the trace-free part of second fundamental form is given to you is solvability of this system of equations. So this is a linear equation. I'll tell you a bit more about in a moment. It's a type of a twistor equation, and this equation is a nonlinear constraint. And the second equation is so this is what we get from the Gauss-Kodazzi equations. One of them is algebraic, one of them is differential. You can then show that given a solution to these equations, you see, to reconstruct the embedding, you need to find the conformal factor and this trace part of the second fundamental form. For any given solution, there is a six-dimensional space of pairs, omega and k hats, so six-dimensional family of embeddings. And the second result is once you find such an embedding, which is generic in the sense that the rank of the second fundamental form is maximal at the point, then this embedding in the neighborhood of this point is rigid up to conformal transformation. So all you can do is to, given an embedding, you can apply a conformal, not just a rescaling, but action of a conformal group on the ambient space. That will give you a new embedding, but it's no more. But now I want to talk about this theorem 1. See, ideally, you would like to solve this twistor equation. So find all the space-times which admit such a sigma with such a constraint. And that is something which we could not do. And the closest, to my mind, one come about doing this is what I think is a very seminal work of Jurek from the 90s, where he solved the, well, admittedly simpler twistor equation. So this is, a twistor equation would be for valence 1 spinor. It would be grad A prime A omega B equals 0. Roger would have talked about this twistor equation. I think Felipe, using his notation and language, also talked about this twistor equation. What Jurek has done is he classified and found all Lorentzian spacetimes which admit a solution. So we would like to be able to do it with our equation, but we cannot. I mean, it's more complicated and it has these algebraic constraints. So instead, we want to find some obstructions. We want to say, given a space-time, do we have a hope of finding a solution of these twistor equations, even though we cannot find it explicitly? So local curvature obstructions, and to write them down, I'm going to use standard, well, by now standard notation going back to Roger, but really hidden in 19th century invariant theory. So you see this Weil spinor, psi A, B, C, D. Algebraically, you can think of it as a binary quartic. You see, a Weil spinor is a homogeneous polynomial of degree 4 in 2 variables. And this is something of classical algebraic geometers in 19th century were interested in. How do you construct invariants of quartics? There are, it turns out, only 2 such invariants. One is quadratic in the coefficients and one is cubic, the I and J. They both have interesting interpretation in projective geometry using cross ratio, so ratios George talked about this morning. For us in GR, they used to classify it or detect the algebraically special type. If a Weil spinor has a repeated principal null directions, then the quartic has a repeated root, and that will happen if this combination of I and J, that's called a discriminant, if that vanishes. Now, a result, well, we could prove is that a conformal isometric embedding of class 1 can exist only if, so it's a necessary condition, I and j are real. See, the spin frames you choose to compute this I and j will not necessarily be real, but nevertheless it can be that I and j are real, and that's what you need. So from this you deduce that the Kerr metric doesn't admit such an embedding of class 1, because for the Kerr metric you find that j is complex. You could push these obstructions and the theory to other signatures. I mean, I'll spare you the neutral one, that's a bit exotic, but Riemannian is interesting. So these obstructions were thought of properly are applicable to Riemannian signature. See what happens there, the Val spinor Val tensor decomposes into a self-dual and anti-self-dual part, and you can associate I and j to both self-dual and anti-self-dual parts, so they're independent. And what you then find, so that's the kind of Riemannian counterpart of proposition 1, is that the necessary conditions for a local conformal embedding is that the i's and the j's which you compute from these Val spinors are equal. There's a self-dual I is anti-self-dual I, and the same for j. See, so from there you deduce that if a Riemannian manifold has a self-dual Val tensor, so then there is a class of Riemannian manifolds people look at in physics with this property, they called gravitational instantons, they often self-dual. If that happens, then an embedding of this type only exists if the manifold is conformally flat. And this is because for self-dual manifolds, the I and the j vanish identically. So to satisfy these obstructions, I prime and j prime have to vanish identically, but that would mean that the whole Val tensor would have to vanish. Okay, so for example, CP2 with this Fubini-Studi metric, I mean, is a self-dual manifold. The proposition 2 tells you that therefore it cannot be conformally embedded in R5. It might be conformally embedded in higher dimensions. We know how to embed it in R7, and we don't know, as an open problem, whether CP2 can be conformally embedded in R6. Leaving that aside, I'll move to a familiar class of spherically symmetric spacetime. So now I'm kind of heading towards physics with this. So I have a static spherically symmetric Lorentzian spacetime in dimension 4, and I'm assuming that the function v, which depends only on r in this spacetime, has only a finite number of simple zeros. So that would include a Schwarzschild metric, it would include the Reist-Nordström metric, but it would exclude the extreme Reist-Nordström metric. We can prove that if the conformal embedding, if a conformal embedding of such a spacetime exists, and if it is global of at least one sphere of symmetry, so on a sphere where SO3 group acts, then the following thing happens. The second fundamental form trace-free part is spherically symmetric, and the embedding only depends on two arbitrary functions. So it's, this one is not rigid. There is some functional degrees of freedom. Proof of the first part is what goes under GPH formalism. That stands for Gerolstein-Penrose, and some harmonic analysis, and Koshikova-Levskaya with the real analytic assumptions for part 2. Now, let me give you examples of such embeddings, still for general function v. See, so I'll be very concrete now. I want to embed this spacetime, and you give me a v of your choosing, and I want to embed it in a flat 4+1 dimensional Minkowski space. So I'm writing this flat 4+1 dimensional Minkowski space in this form. I mean, there is a choice of flat coordinates, and I've I pick the same coordinates on the two spheres, so theta and phi are the same here and there, and I want to match this with that. And the first thing I learn, because I want to match the metrics on the two spheres, is I learn about what the conformal factor should be. So that's done. And once I do that, I've sorted out the two sphere, and I need to worry about this part of the metric and this part of the ambient metric. And because of the form of the conformal factor, I need to find an isometric embedding of a conformally rescaled part of Schwarzschild in a patch of ADS3. And so that's a very concrete problem which I can now attack for any given V with the assumptions about its simple zeros. And what I'm going to present you will be the unique static, spherically symmetric global embedding. So I'm going to construct an embedding, and it'll be global, and by some uniqueness theorems we prove it's the only one. And it'll look not penetrable, but it's not too bad. I mean, if you work with it, it's not too bad. So here is how I do it very explicitly. And again, I just come back here. My job now is to embed this isometrically in that. So I need to tell you how capital T, capital X, and capital R depend on little t and little r. And that's, let's say, the ansatz I make. It involves hyperbolic functions. It involves some unspecified parameter a, and involves a function h. Now, what I get from the isometric embedding condition is a formula for what this h should be. And you see, I haven't specified v, so it's given by an integral. Now comes my assumption about v's having only simple zeros. You see, the thing I should worry about in this formula is if I divide by v in the denominator. So if v equals 0 in the denominator, it looks like this blows up. But I have this parameter a to play with, and I can claim that. So I start from infinity and I go down in r until I hit the first zero of v. Let's say it's at r bar. What I can do is I can choose the parameter a to be plus or minus a half v prime evaluated at this zero, and that's, if you do a calculation, that's precisely the surface gravity of the killing horizon of this metric. And by having made this choice for a, I can convince myself that the singularity has been removed. So I've cured one problem at the first zero, but then suddenly if there are more zeros, then I'm dead, because you see I'll hit another singularity at the second zero of v, and I have no a to play with because it has been fixed, so the embeddings, at least the way we do it, will not work. On the other end of the spectrum, if r tends to infinity and v tends to identity, so the metric is asymptotically flat, then asymptotically the conformal factor tends to 1. So it's discouraging if there are more than 2 zeros of v, but it looks okay if there is only 1 zero. So what is the metric, static, spherically symmetric, where v has only 1 zero? Well, that will be the Schwarzschild metric, where v is 1 minus 2m over r. Then the embedding is given explicitly by this. So I need to tell you how capital R depends on little r, and it's an exponential of an integral of a ratio of these two functions. So it's not, it's not an elliptic function. It has, you might say, it has a chance of being one because it has some cubes and square roots, but it is not. But nevertheless, it is regular. It's a completely regular function, regular at r equals 2m, and it goes all the way down to singularity. So you've constructed this embedding. You might say, well, there is more to Schwarzschild metric that you can see from writing a coordinate formula, because I mean, Roger tells us that Schwarzschild is can be compactified, and we should look at the scry, the asymptotic infinities. You can therefore ask what happens to the scries under this embedding. You see, Schwarzschild has scry plus and scry minus, and so does the 4 plus 1 dimensional Minkowski space. So you expect the scry plus and scry minus of Schwarzschild to be mapped into some regions of scry plus and scry minus in the Minkowski space. And what turns out for our embedding is that it's kind of degenerate maps. So the whole of scry minus is mapped to a point on the scry minus of, did I have my minus and plus? Yeah, it does look like I have my pluses and minuses other way around. But the whole of scry minus is mapped to a point on scry minus, the same with whole of scry plus. So the embedding doesn't extend to a compactification. Now a bit of kind of quantum theory, so maybe change a gear a bit. I mean, I refer to your knowledge which exceeds my knowledge of the Hawking effect, in that the temperature measured by an asymptotic observer is for a black hole which has at least a Killing horizon and a surface gravity, is given by a surface gravity divided by 2 pi. So that's a definition of surface gravity at the horizon, and that's a known effect. There is another effect which is discovered at the same time, but this refers to a quantum field theory on flat spacetime. It's known as the Unruh effect, and that is that the observer moving with a constant acceleration in Minkowski space also measures some temperature, which is related to the what we could call a surface gravity, but of a Rindler horizon. So the way, if you want to have a sense of where this effect comes from, is you take a Minkowski metric and you write it in accelerating in Rindler coordinates, and it is in these coordinates you study the wave equation and decompose into positive and negative frequencies. That's one way to analyze it. Now, back in late 90s, Deezer and Levin have shown that for isometric embeddings, the Hawking temperature of mg equals the Unruh temperature of an embedding as long as the embedding is global, so it extends through a horizon. And that was an interesting paper which was then verified for many known solutions. So we can make similar claim, or identical claim, for conformal embeddings of Schwarzschild. But to justify this claim, I need to kind of make some comments about the validity of this Hawking formula. You see, and what needs to be said is that, well, conformally, so a conformal embedding of Schwarzschild is the same what isometric embedding of conformal Schwarzschild. I think I'm short-changed. I think you're, or am I? This is my last slide, so I'll be okay. But you see, so mg hat is not Einstein. I claim that this formula nevertheless applies because Hawking effect is kinematical. I mean, no, it does require a horizon to exist, but it doesn't use the Einstein equations. You can also argue, and we do it by calculation, that the notion and the formula for surface gravity is also conformally invariant, as long as both the conformal factor and its gradient are regular on the horizon, and omega doesn't depend on time, and it tends to identity that's needed for normalization where r goes to infinity. And with 1 and 2 sorted, you then calculate and show that the trajectory of the Schwarzschild observer, integral curve of d by dt, leads to a hyperbola in R41, which is a trajectory of an accelerating observer, and the numbers involved are such that the temperatures can be compared and they in fact equal. I mean, there is a technicality with taking a limit where, yes.
So this is trajectory for which trajectory? Spinning the curve is many trajectories.
Well, what I'm doing is I'm looking at the, I'm fixing all the coordinates, if you like, r, theta, and phi, and vary t. Okay, so I've, in fact, actually, no, killing vector doesn't have many. It has a one parameter. If you give me a point, then through this point, I zoom a trajectory.
I see. So to a point which in Schwarzschild corresponds to r, the acceleration in this bigger space is alpha.
Correct.
Okay.
Yeah. Right. So where do we go with this? I mean, you can write some of these embeddings for higher dimensional black holes, and that is in our algebra. More interestingly, study the causal properties of asymptotically flat spacetimes using these embeddings. Peter Cameron, as a work in progress, he actually did give a talk about it last week in France. So it's big progress in this project. I mean, in pure maths, you might want to develop an obstruction theory, really go deeply into these holonomy problems. How can you tell whether there exist embeddings in fewer than maximal dimensions? And we spent some time with Paul thinking of, but unsuccessfully, of finding a global conformal embedding of extreme Reist-Nordstrom. See, our way of doing it doesn't work because this one has a double zero, but it's not to say that there isn't another one, and it'll be interesting. I'm told to find those for extreme black holes. Find or rule out a conformal isometric embedding of a complex projective plane in R6. And finally, and that's the kind of subject of this preprint I listed on the first slide, understand the embeddings for gravitational instantons. So we can show now that Eguchi-Hansen and the self-dual Taub-Nut instanton can be explicitly isometrically embedded in R8, but not in R6. Again, we don't know what the embedding class is, and that's where I stop.
Thank you. So we have really big delay.
Well, it's not my delay.
Well, everybody contributes a little. Some people more, some people less. Okay. So are there questions or comments? Yeah.
What happens to the left-hand side scri plus and scri minus of Kruskal under your embedding?
See, on the top of my memory, I'd answer that they are mapped to exactly the same 2 points which the right-hand side are. Because for Minkowski space, of course, you don't have the left-hand side. There's George there.
Yeah, so given the Hawking, I think has an argument for their temperature based on going into Euclidean.
Yes.
If you did this whole thing over, pardon me, if you did this whole thing over for a complex Schwarzschild,
Yeah.
could you sort of incorporate both ideas in one thing?
Well, I'm not sure about complex, but I can tell you about Euclidean Schwarzschild, because there, you see, what happens there, unlike the Lorentzian Schwarzschild, Euclidean Schwarzschild is regular, and it can be regularly embedded, conformally embedded in R5. And again, surface gravity comes into this, but we knew it would, because in the Euclidean derivation, it is the surface gravity which gives you the right periodicity of the Euclidean time, which you need for regularity. So in our language, that means that the embedding of Euclidean Schwarzschild in R5 is only regular if the surface gravity, if the surface gravity and Euclidean time are tuned the way they should be.
Let us thank the speaker again.